And I did check the audio of the one yesterday, and you can only hear me. You can't hear anybody in the audience. So Trevor or whoever made a comment yesterday that he was worried about is safe. Okay, so this is the rest of transportation. So we started the geometric design, and we're going to finish that up today and then talk about pavement design, traffic capacity, traffic control devices, and transportation planning. All right, so this is kind of a little bit of a carry-on from the surveying. So that you probably remember this more so from surveying than you do transportation, but possibly from both. So this is from page 300 in the FE reference book. We talked yesterday about how to design the minimum curve length, accounting for a stopping site distance. So once you have that curve length, or if the curve length itself has been identified, then you can go through and do your surveying type calculation. So that's L, this curve length here. So for a vertical curve, you have a back tangent with a defined grade, and then you have a forward tangent with another defined grade. And so this is showing for a crest curve. If you had a sag curve, then you would have a negative initial grade and a positive later grade, and then you're fitting a parabola to it. And so the key points, so where the curves, we got the curve here. So where it departs that tangent, that's the PVC, so the point of vertical curvature where it starts. You've got the PVT where it ends, and then the PVI up here is where the those two tangents intersect. And so that L, again, I think this question came up yesterday, so that L is not measured along the curve, the L is measured in the horizontal plane. The main equations that we are going to use are this one, which I've got a red arrow on the other side I now see. So we have a curve elevation. So this equation allows you to calculate the point, the elevation of any point along the curve. And so the way I like to visualize one of these curves is if you've got a XY, set of XY axes, so your Y is going to be the elevation because you're standing on the side of the road looking at the road from the side. So anything in the Y direction is going to be the elevation. And then your X direction is just going to be a station. So we talked about stationing yesterday. It's an X value that corresponds to the station, or just a distance along the center line. So looking down here at this curve equation, this Y PVC, that would be the elevation of this PVC. So it's telling us what's the elevation of the start of that curve. This second term, G1 times X, so we've got the grade, we're just multiplying the grade times the X distance, so you can see X right here. So if we're interested in what's the elevation of that particular point right there, we're by taking the grade times that X distance, that is going to project, I guess I made a mistake. That point is not on the curve that I just drew right there. Well, can I erase it? There we go. So the point is actually down here that we're interested in. So starting out at this is the first term, so G1 times X is giving us this distance, so this offset distance here. So we start out at that PVC elevation, we jump up to G1 times X, and then this last term, AX squared, is going to be that Y distance that's shown there. So that's going to end up getting subtracted so that the elevation that you end up with is on that curve. And so down here, this is A that gets plugged in here. So again, that's the main equation that's used in these. There's a couple of other relationships that are important. Let me jump over to this diagram because it's the same whether it's a crest or a sag. So I already indicated that this total curve length is L. Another important feature, if we start here at the PVI or the VPI and trace this up, this distance is L over 2 and this distance is L over 2. So they call these equal tangent vertical curves, and that's an important property because a lot of times the PVI, they'll give you that it's at station 1000. And so then if you know that the curve length is 600, then the station of your PVC is just going to be your PVI station minus L over 2. Let me move this down. So PVC station is PVI station minus L over 2. Likewise, the PVT station is equal to PVI plus L over 2. So those are two relationships that they don't give you in the FE reference manual, but could come in handy just knowing those basic relationships. All right, so let's look at, I think, nope, no example yet. Notice down here, this equation, K equals LA. So K factor is commonly used in roadway design. It's kind of the shortcut method. This design speed, so we talked yesterday about how stopping sight distance affects the curve length. And for any given design speed, this table is also giving us the stopping sight distance. This table is not given in the FE handbook, but I have seen example problems where they've given it to you and asked you to figure out how to use it. So if you know the design speed for your roadway is, say, 60 miles an hour, this K factor, so if it's a crest curve, L equals KA, we can calculate the length. So for a crest curve, we know K is equal to 151. And then A is that same algebraic difference that we were looking at yesterday. So if we had +3 and -2, that would be an algebraic difference of 5. So we just take 151 times 5. And what is that? 755. So that would give us a crest vertical curve length of 755. And again, that's measured in the horizontal plane. And if it's a sag curve, recall that there was different criteria for the sag curve. If we had -4 and +3, this L equals KA. We now have a different value of K since it's a sag curve. That's going to be 136, and then our algebraic difference in our grades is going to be 7. And that would give you 2. Yeah, I'm not going to try to do that in my head. 952. Thank you. So just realize that if they gave you a K factor, this equation down here on the bottom, it's shown as K equals LA, but you could rearrange it to solve for the curve length if they give you that K factor. Or if they gave you this table and asked you to design the curve length for a given design speed. Main thing is realizing is it crest or sag. So most of the time on these problems, they'll give you a curve length. They'll give you the grades, they'll give you the station of and elevation of the PVI, and then they'll ask you to find some other piece of information. Another equation that was back on that slide that is sometimes used is the, let's see, this right here. So horizontal distance to min and max elevation on the curve. So if it's a crest curve, that's going to give you that horizontal distance to the high point on the curve. And if it's a sag curve, it'll give you to the lowest point on the curve. And then once you find that X distance, you can plug that into these values of X down here to solve for the corresponding elevation. So let's look at an example that will hopefully make things a little clearer. So we have this is not an FE style example. The same as yesterday. I've kind of got more involved ones versus FE style ones. We have a back tangent with a plus 7% grade that meets a forward tangent with a negative 5% grade on a vertical alignment. We're given a horizontal curve length of 1150, and we're given a PVI, station, and elevation. So is this a crest curve or a sag curve? We've got a positive 7% and a negative 5%. And so our given information, L equals 1150. We try to write a little bit here. And then got our PVC, PVI, PVT. So our PVI, our station, is 20 plus 35. And our elevation is 250. So we're asked to find a whole bunch of different things. Again, visualizing our coordinate system that starts at the PVC elevation and station or X distance. So first we want to find the station and elevation of the PVC. So our PVC station, again, this is a relationship that's not given, but we can assume that if we drop a line down from the PVI, that this is going to be L over 2 and this is going to be L over 2. So if we started our PVI station of 2035 and then subtract 1150 over 2, this will give us our PVC station. Anybody calculating for me? I don't have these. So it'd be 14 plus 60. And then similarly, PVT station. Oh, it doesn't want to erase. It's going to be the same thing, only adding. $26.60, no, $26.10. All right, so the stations are the easy ones. Now the elevations. So our PVC station, or sorry, PVC elevation. Our starting point is our elevation at our PVI. So we've got PVI elevation, and this is just more of a mathematically realizing that this makes sense. So we know that our PVC elevation is going to be greater than or less than our PVC. Sorry. PVC relative to PVI is going to be greater or lower. It's going to be lower, so we need to subtract. And so the change, so if I were to draw a line over here, we want to know what is this change in elevation if we take our grade of 7% times that horizontal distance of L over 2, that would give us that delta Y. So this would be minus G1 times L over 2. So G1 is the grade, that slope, and then L over 2 is the X distance. So multiplying those will give us the difference in Y. So our starting elevation, don't get your elevations and your stations confused as you're going through these. We've got 250 minus grade here needs to be in a lowercase or in a decimal format. So the lowercase g, you're not told back on the equation sheet that this is in decimal format, but let's see. Yeah, I don't know that there's any clues as to what that is, but if you use it as a whole number, your answer should not make sense. So use some common sense. So 0.07 times 1150 over 2. Does that give you? So that seems reasonable. And then now our PVT elevation relative to the PVI. So we're still using PVI as our base. So are we going to, does this PVT elevation, is it going to be below or above the PVI?
I think below.
Yeah, it's still going to be below. So we're going to subtract G2 times L over 2. So we'll have 250 minus 0. And I'm subtracting the absolute value, because if I subtract a negative, that's going to end up being a positive term, and then it's no longer going to be below it. So again, a little common sense. Point what? And that would make sense that that one's not as low, because you're going the same horizontal distance, but it's at a less, not as steep of a slope, so you're going to end up at a higher elevation than the PVC. All right, so that takes care of the first one, that takes care of the second one. So next we want to find what is the curve elevation at station 21 plus 35. So this is where we're going to use the elevation equation. I wish I had more room here. I'm going to do the old draw a line to create some writing space. So in order to calculate, to use that elevation equation for y, we need to figure out what is the x distance to this point. So station 21 plus 35, where is it going to be relative to the PVI? Is it going to be left of it or right of it? So 21 plus 35, is it left or right of the PVI? It's going to be to the right. So it's going to be how far right? It's going to be 100 feet to the right, because our PVI is at 20 plus 35. We're interested in the elevation at 21 plus 35, so that's 100 feet to the right. So the x value that we plug in, we need to find x. We don't plug in 2135 because we're not 2,135 feet from the beginning of the curve, because the station of the beginning of the curve, we just calculated it as 14 plus 60. So if this is the point we're trying to find, we only want to know what is this horizontal distance over to that point. So that calculation is going to be 2135 minus 1460, because the value of x, or the station at the PVC, is 1460. So we take the station here minus the station at our PVC, and that gives us the difference, which is the value of x. So then plugging that into, I'm going to jump back just to show you which equation we're using. So this curve elevation equation down here that I've pointed at multiple times, curve elevation is the elevation on the curve. And here it is in its expanded form out here. So we already know YPVC, that's the elevation of the PVC. We've already calculated that. We know G1, we just calculated X. We know G2, we know G1, we know L. So we have all the information we need to calculate the elevation at that point. So I'm not going to write the variables out. I'm going to go ahead and put in what it should be. So YPVC, that's the 209.8 that we just calculated down here. And then plus G1, which is 0.07 times X. Actually, we didn't finish that. What's 2135 minus 1460? So 0.07 times 675. And then plus G2 minus G1. So here we do maintain signs. G2 minus G1 over 2L times x squared, which is 675 squared. I know that's a lot to plug in.
You're wrong, but 233.3.
Why do you think it's wrong?
I'm not sure if I did the A calculation.
What'd you get? Same thing? Okay, so reasonableness, 233.3 feet. Whatever this calculation comes out to be, what should it absolutely be between? It cannot be less than what? Yeah, so there's no way it can be lower than our PVT out here, which we know is this 221. So that gives us a lower bound. What's our upper bound? Yeah, the 250. We know that it has to be somewhere between the elevation of our PVI and our PVT. Okay, so that takes care of that one. So we found the curve elevation. And then the last one, I used blue. So I'll do the last one to find the station and elevation of the high or low point. So this is a crest curve, so we're going to be finding the high point. So jumping back a couple slides, you have the XM is equal to G1L over G2 minus G1. So this is just plugging in grades and lengths, given information. We've got 0.07 times 1150 over negative 0.05 minus 0.07.
What was the grades that were in your list?
Well, so it will go ahead and calculate it the right way and tell me what you get. $671. So actually in this instance, since you've got the grade on the top and the bottom, even if you plug it in as full percentages, you should still get that same answer.
Is it negative?
Oh, I got the equation wrong. Somebody's supposed to be paying attention. The bottom is G1 minus G2. G1 minus G2. So this would be 0.07 minus a negative becomes a positive. So we'll take it.
No, same answer. Yeah, I mean, that would make sense, right? corner of the property, whatever that is, add subtraction properties.
Oh, was it negative?
Yeah, negative.
Okay, negative 0.12 on the bottom. Okay. What was it, 671? So this equation, the G wouldn't make sense because the difference in the decimal should cancel out. But on the previous problem, if you use the wrong values of G, your answer is no longer going to be bounded by those elevation points that we just identified. So this gives us the X distance. So if we wanted to calculate the station of the high point, how would we find that? What would we do with that 671?
That'd just be half of the difference between the PVT and the PVC subtracted from the PVT.
Sort of, but you way overcomplicated it. So what do we actually, so the 671 is measured from, reference from what point? It's 670 feet, 671 feet from where? From the PVC. So we already know the station of the PVC, right?
So it's just PVC plus.
Yes, we just take the 1460 plus 671, and that gives us the station of the high point. 21. 2131. Plus 31. And I'm not going to walk through the calculation, but the last piece is what's the elevation of that point. So we know how far it is from X. We know what its station is. How would we find the elevation? What equation would we use? Is this point still on the curve?
Isn't it just 250?
No, because the VPI or the PVI, where is that relative to the curve? The PVI is an actual intersection
Oh, okay. Yeah.
of these. So PVI is either way up in the air or way down in the ground if it's a sag curve. Like you can't physically go to that point. So the PVI elevation is not the elevation of the curve at that location. So up here, we use this Y equation to calculate the elevation at an X equals 675. So we would use that exact same equation, only instead of 675, we would use 671. Because the equation of the parabola is what it is. It's just you're plugging in different values of X. And so in Excel, you could have all your station values, you could have a row of station values, and then you could have a single column calculating what's the elevation that is only changing with the value of X that's right next to it. So for any X, so we could plug in any distance of X and it would give us what's the specific point. And then what do you think happens when X is equal to your curve length? If the X you plug in is equal to 1150 in this example, what elevation do you think that's going to give you?
0.
Nope.
Just whatever.
So it'd be the elevation of your PVT, which we calculated over here as 2221.3. So we went through all this for a crest curve. What do you think we would do if this was instead a sag curve? What all changes? Will our PVC and PVT station calculations change? Will either of these change? Nope, nothing changes there. What about here? The PVC, PVT elevation. So those will change because we need those to be higher. And so I'm kind of implicitly assuming that we're using the absolute value of those and ignoring and just realizing that whatever we calculate needs to be higher or lower. What about the elevation equation? Y equals. Does anything change there? So we don't explicitly change it, but if we follow that this is G1, G1 is going to become negative because it'll be a downslope. And then G2 and G1, those will get flip-flopped and that overall term will become positive. So the only explicit change that you make when going from a crest to a sag curve is with how you're calculating your elevations. But still, if you apply some common sense that, hey, I know this resulting calculation needs to be higher or lower than my PVI, then it shouldn't be that big of a deal. So again, FE style question, they're going to ask you one of these elements. So I did a little bit more deep of a dive than necessary. All right, so horizontal curves. So vertical curves, we're standing on the side of the road looking at the profile of the road itself. Horizontal curve, we're now plan view, flying over top, looking down on the roadway itself. This is the information from the page 301 in the manual. So the roadway itself, we've got our PC. Don't ask me why it's not HPC, HPI, HPT to differentiate horizontal from vertical. I didn't write the book. But we've got PC, which is the point of curvature. We have the PI, which is the intersection of the back tangent. So we've got our back tangent. We've got our forward tangent. Only here, there's no such thing as a grade because we're looking down on it. So the only information we have about the tangents are the distance. And then where the curve itself comes back into contact with the tangent is the PT, or the point of tangency. So the cars are actually traveling along the arc. For a vertical curve, that's a parabola. For a horizontal curve, it's just an arc. It's just a portion of a circle, which allows us to have a radius. So if we were to zoom out and we were in CAD or something, we could continue this circle on around, and with this being the center of the circle. So we're just kind of subtending a portion of a circle of a defined radius. Let's see. Did I update this picture? Okay, so if you look at the diagram here, so this is maybe the most important well, one of the most important features, but the length of the curve itself from PC to PT. How do you think that's measured in this diagram?
The arc length of I.
So yes, it's the arc length. So this from PC to PT, this is what the vehicle drives. That's the length that we're interested in. That is L. Do not get it confused with this, which is labeled the LC. So LC over here is the length of the long cord, which we don't really care about unless they ask you to calculate it, but it's not a value that we care that much about from a transportation engineering standpoint. But so realize that L is not actually labeled on that diagram. So I've got two additional equations up here on the top right that are not given that could be potentially important. And I see now that they're missing. So there should be an STA there for station. And this is possibly one of the most confusing concepts, even when you go through intro to transportation, as well as geomatics, since this is kind of covered in geomatics as well. So whenever you're initially laying out a roadway, this tangent section is extending all the way down here, and then you get to the point where the road needs to turn. And so this tangent all the way up to the PI, and this tangent is already defined. And so the surveyors can lay out stationing along these tangents, and so you'll have a PI station that has been calculated. So let's say that's 10,000. What we want to be able to do from a roadway layout standpoint is go back, figure out what is the PC station, and then lay out, because the surveyors, they need to lay out and stake out this roadway along the center line, because that's how all the construction happens, is along the center line of the roadway. So in order to calculate the PC station, we've got this T value here, a tangent. So if we know our PI station, we can subtract that tangent distance to get us the PC station, right? So that's what this equation up here is. So PC is equal to PI minus T. So once we know the PC station, because we want the stationing along the curve, if we take our PC station and add L, the curve length, that is how we get to our PT station. That makes sense. If you were to walk, I have a hard time pointing with the, if you were to walk here to the PI to the PT along the tangents, would you walk the same distance as if you were walking from the PC to the PT along the curve? You would not, right? Everybody agree with that? So that's why you cannot, to get the PT station, you cannot take the PI station, add T, and get the same station, right? Because it only matters along the center line. That's how we're going to build the roadway. So even though you could add T to the PI station, it's going to give you a number that has some meaning, but it is not the actual PT station with the roadway laid out along the center line. So these two equations up here are kind of fundamental understanding of these diagrams, and it's certainly something that they could try to trick you up on. But pretty much anything, they give you all of these equations here. So it's more a task of figuring out which equation you want to use and realizing what information they do or do not give you. So look at this example. Horizontal curve is laid out with the PI, the point of intersection station at 22 plus 0, 0, a radius of 1,000 feet, and an intersection angle of 120 degrees. What is the intersection angle in this diagram? Well, what variable is it? So it's I. So I is this intersection angle down here, and it's basically this entire distance, the entire angle that's being turned from the PC to the PT. So just doing a quick sketch. Let's say you can draw your snow cone. For some reason, I was talking about ice cream yesterday, so today I'm going to talk about snow cone with a hat on it. So we got PC, we got PI, we got PT. Radius is 1,000, and then this angle is 120 degrees. Obviously, I did not draw this to scale. And our PI is at station 22 plus 0, 0. One of the biggest mistakes, even when I teach Intro to Transportation, horizontal curves and vertical curves are on the same test. Surprisingly, a number of students try to use vertical curve equations for horizontal curves and vice versa. So the biggest indication is if you have any information about an elevation, then it's going to be a vertical curve. Because here for horizontal curves, we're just looking straight down on it. We don't care if it actually has elevation change. We don't account for that in the horizontal curve design. That would be accounted for in the vertical curve design. So if you have elevation information that is meaningful, then it's a vertical curve. Okay, so first we're asked to find the degree of curve. So what is degree of curve from the previous, what is that equation? what given value can be used for that? What's that? So the first equation is R equals 5729.58 over D. So D is what we're trying to find, so we can rearrange 5729.58 divided by our radius of 1,000. It's going to give us 572.958 feet for our degree curve, which is not in feet. Yeah, I can't do math. That divided by 1,000 is 5.72, and this is in degrees. 5.72. Trying to decide how many digits to keep. I'll keep them all. So that's in degrees. So now we want to find the tangent distance. What equation can we use for tangent distance? So tangent distance is t. So the third equation, we can use r tan I over 2. We got 1,000 times the tangent. We were given I, which is 120 over 2. I definitely can't do trig functions in my head. So I give you
1,732.
okay. What about the length of curve? So what variable is length of curve? Is it L or LC? It's L. So long chord, length of curve, unfortunately, are both LC. So make sure you pick the right one. So L. So we've got two different forms of the equation. Let's do the RI times pi over 180. So we've got 1,000 times 120 times pi over 180. Yes. Yeah, because our 120 is in degrees. Okay. So then our PC stations, so these were what we were not given. I'll rewrite them here since they're not on the slot on the sheet. We got PC is equal to PI minus T. So we know our PI is 2,200. We just calculated T is 1732. Or 68. 4 plus 68. And then our PT station is PC plus L. So we know PC, we just calculated it, it's 468. We just calculated L as 2094. $25 plus 62. Is that right? So these are much simpler calculations than the vertical curves, for sure. They give you just about every equation you could possibly need, except for the PC and PT station. So whenever you're designing a vertical curve, or sorry, designing a horizontal curve, the radius value is going to control how sharp the curve is. So we went through the stopping sight distance calculation yesterday, where think about a curve radius of infinity is essentially a straight line, and you're not going to have any problem seeing around the curve. That's going to be the most expensive to construct. And so you're always wanting to find the minimal curve radius, because that's what's going to allow you to fit the terrain if you're trying to kind of go between valleys and minimizing cut and fill for a construction project. So designing the curve radius is the next element. Oh no, I forgot I pulled this problem in. This was from the FE exam book. So this is a little bit different style of a horizontal curve design. So here we have the area inside the quadrilateral between the PC, the PI, the PT, and O equal to that large number. The shaded area between the circular curve and the tangents is most nearly what? So how in the world would we solve this problem? Anybody? So what do you think we can use what's that? So this one has almost nothing to do with horizontal curve. So you need horizontal curve elements to get to the answer. But really remember that this is a portion of a circle, right? With a radius or a center point around O. And so they've given us what's that total area bounded by that quadrilateral. So if we can solve for just what's this area in here and subtract it, that'll give us the shaded area. So what do we need to know in addition to the radius? What do we need to know, or how can we find what's the area there? So if we know, we could calculate with the radius what is the total area of the circle, the entire circle, right? And then we would, if we knew this angle, we would know what portion out of 360 to be able to take the proportion of that. And that would give us that total area in there, right? So do we know this angle?
Saying that the beginning is the same as that.
You tell me. So look at your diagram for horizontal curves.
Yeah, it is.
So this is the same. So they're both labeled as I. Oops, should be a line. So area of a circle is pi r squared. And then we want to take a portion. So it would be 36 degrees, 48 minutes out of 360, right? Where R is 500. I should have written that in there. Get an answer?
$80,285.
So if we take 83,164 minus that value, looks like the answer is going to be A.
2879.
So that's a perfect example of kind of understanding the fundamentals of what you're working with. So this is, you clearly need to refer to your horizontal curve information about this to recognize that those two angles are equal. But then from that point forward, it's just more of a math exercise. All right, so now moving on to designing the R, the radius of the curve, and I don't think I have an example for this, no. You're given these two equations, so super elevation, looking at the way I like to describe this equation, if you're going around a curve, what's on the right side is pushing you out of the curve. So the higher your speed, the higher that force is going to be trying to push you out of the curve. And then the E is the super elevation, and then the road friction is counteracting that. And so you always want the left side of this equation to be greater than the right side of this equation, or else people are going to be sliding out of the roadway. And so you can design, F is a friction factor that's usually given in a problem if they wanted you to use this equation. E is super elevation as a percentage, and then this 0.01 is just converting it to a decimal. But super elevation is kind of how much pitch you have. And then the V squared, so you've got your speed squared divided by 15 times the radius. So as your speed increases, that right side is increasing. Same thing as your R decreases. So as your radius gets smaller and smaller and smaller, that's also going to increase that right side of the equation. So this can certainly be rearranged. If you're given all those values, you can rearrange it to solve for, to be able to solve for R. Which is most likely how they would have you use it. But just realize that you can rearrange that and solve for your curve radius. And I would ignore this. So they give you this. Do they still give you this? Or did I mess up? Not. Nope, it's still in there. I've never seen a question on it. And I'm not even going to spend time explaining it because there's other things that are higher probability of being covered. All right, I think it's the last part of the topic 1, which is geometric design, is looking at intersection sight distance. So this is on page 299. And what's really going on here that they want you to be aware of, I think, and this upper right is what you get. These diagrams down here are kind of what I'm using to explain. So imagine you are sitting at a stop sign. So this is a two-way stop controlled approach. So you have I'll even draw it in red. So you've got your stop sign here. And likewise, you would have one over on this side that I'm going to draw as a circle to simplify things. But you're the vehicle that is sitting here. Traffic on the major road. So this is the major road. Traffic going that direction is not stopping. So you're kind of looking for a gap in the traffic. And so intersection sight distance is defining how far upstream do you need to be able to see the vehicles. So the faster the vehicles are going on the major road, then the farther you need to be able to see, because they're approaching at such a high speed, you need to be able to pick them up farther away to give you enough time to pull out, either drive straight across, pull out and turn left, or pull out and turn right. So on this diagram, the intersection sight distance is measured from basically where your car is to where you need to be able to see the approaching car back here. And so this equation looks very similar to the stopping sight distance. In fact, on that page, it's right below the stopping sight distance. What's this 1.47 doing? It's just converting speed from miles per hour to feet per second, because this V major is the design speed of the major roadway in miles per hour. And then this T sub G value, this is the time gap needed for the vehicle entering the roadway in seconds. So we got speed miles per hour, time in seconds. That 1.47 is converting the miles per hour to feet per second, which allows us to get an intersection sight distance measured in feet. So if you are this vehicle and you're turning right, you could care less about the traffic that's coming from the right, correct? You're just worried about these vehicles that are coming this direction, because you're going to turn right and just accelerate up to the speed of traffic. But if you're trying to turn left, if you're trying to take this maneuver, you have to check both conditions. You have to make sure there's enough time coming from the left, and you have to make sure there's enough time for the traffic coming from the right. So once you calculate that intersection sight distance, this sight triangle, because you're the driver, you're sitting back here, your line of sight is diagonally. So the intersection sight distance is measured along the roadway, but your line of sight is a straight line distance. So this is referred to as a clear sight triangle. And so there shouldn't be anything in the road obstructing your view, but there could be a building or something else on the corner that's obstructing your view. And I'm sure you guys have all pulled out of rural roadways where there's a shrub or a tree or something that or a parked car. So you'd want to make sure you don't have any on-street parking that would be blocking that line of sight as well. So again, intersection sight distance, just realize that that's measured along the roadway, and it's accounting for the speed of the vehicles on the major roadway. So that T sub G value, more than likely, they're going to give it to you in a problem because these are slides that refer to various values for that depending on the type of vehicle. So if you're a passenger car versus you're a single truck versus a combination truck, if you're that combination truck sitting at that stop sign, it's going to take a much larger gap in traffic for you to be able to make your turning maneuver. So this example, determine the required intersection sight distance for a stop controlled approach to a 4-lane free flow roadway that doesn't have a median with a posted speed limit of 55 miles an hour. The design vehicle is a single unit truck and there is no grade. So ISD equals 1.47 V times T sub G. So we know what V is. Posted speed limit we're going to use as 55. So then our T sub G value. So we're told that the design vehicle is a single unit truck. And jumping back, again, this is probably beyond the scope of the FE exam, but this table is left turn from a stop. This table is a right turn from a stop. You have to design for the most conservative instance. We actually need to look at both to be able to evaluate the sight triangles. But for the left turn movement, the single unit truck is 9.5 seconds. For a right turn, it's 8.5 seconds. So let's do 9.5. This is for left turn. What's that give you? And then for the right turn, using the 8.5 seconds. So those are the intersection sight distances for this particular vehicle. So now, the hard question. We've got our roadway. So we've got 2 lanes in each direction. This is the vehicle sitting here. We've got our stop bar. So if I'm drawing this intersection sight distance, let me just put a double line. So the 768 feet, is this for, so it's for the left turn movement. Would I draw the 768 feet would it be the blue or would it be the green? And I didn't even draw it correctly because it's supposed to go to here. Is the 768 the blue or the green? It'd be the green, because the left turn movement, we're looking for gaps in traffic here. Realistically, you're looking for both. But then the right turn, so the right turn movement would be the 687 feet. Because the right turn movement, we could care less about the traffic coming from the other direction. And again, the whole purpose of this is if you're constructing a sight triangle, connecting this point back here and this point back here to make sure that there's no obstructions on the roadside. You can also run into issues if you have planters and stuff like that in the median. Those can also block the view for a left turn movement, because if you've got a bunch of shrubs that's wide enough, you've got shrubs down here in the middle. If those are tall enough that they're in that sight triangle, that can create a safety hazard. So this was a conceptual problem. At a two-way stop controlled intersection, the sight distance required for minor street movements is determined by, and this is just something you would have to try to remember from transportation. So your choices are approach sight triangles, departure sight triangles, stopping sight distance, and decision sight distance. What do you think this is? What ones would you eliminate? Which one? I didn't hear what you said. Yeah, so it's not a decision sight distance. Is it a stopping sight distance? So stopping sight distance is for the driver that's already moving. How long is it going to take them to stop? Is that what we're designing for here or not? So we're down to sight triangles. So approach sight triangle versus departure sight triangle. What do you think is the difference between the two? It'd be departure, because we're trying to depart the intersection. So the approach sight triangle is, trying to think of the scenario. It's very rarely used, but it's more so if you're approaching an intersection and it has some curvature, you need to be able to see what's happening. So like the traffic signal heads, if you've got a lot of roadway curvature, you just need to be able to see that there's an intersection there so that you're ready to do whatever could be either stop or looking for other obstacles. So departure sight triangle, because you're trying to depart that intersection. You're sitting there you're already at the intersection, you're trying to leave the intersection. And so you're applying those calculations that we just looked at for the sight triangles. All right, that's all for topic area 1, which is certainly the lengthiest in terms of transportation material. So topic area 2 is pavement system design. So here you're looking at load equivalency factors or equivalent single axle loads, which it's really just LEFs based on the tables that they give you in the FE manual. So these values are given in a table based on given axle weights. You're also interested in calculating the structural number of the pavement, which is a measure of strength based on the layer thicknesses and the given layer coefficients. And it's assumed that the layers that you have for the pavement, based on the information they give you, is an asphalt layer, a base layer, a sub-base layer, and the subgrade, and that's from top to bottom. So this is the table on the left from page 307. So you've got the load equivalency factor, or the LEF. So realize that this table should be a continuous table that has 4 columns. But in order to fit it on the page, this 178 continues up here. So it's just a continuation of the same table. And so you've got gross axle load, LEF, gross axle load, LEF. So this is just a lookup table. So if you know what is the load of your axle is 16,000 pounds. If it's a single axle, then it has a load equivalency factor of 0.623. If that 16,000 is spread across 2 axles acting in tandem together to lighten that load, then it's 0.0472. So that table, that lookup table, is one aspect. The other aspect is this AASHTO structural number equation. So SN is our structural number, and so each of these is a layer. So layer 1, that would be your asphalt. Second term, all the 2 coefficients. Layer 2, that would be your base. Layer 3, that would be your sub-base. So just realize that each of those, so if you have a layer coefficient A times the thickness, you're able to calculate the structural number for each individual layer. So SN1 would be A1, D1. Structural number of layer 2 would be A2, D2, and M if you want to throw in the drainage coefficient. But then summing all those together is what gives you your overall structural number of your pavement. So I think the calculations that you would see on this part should be fairly simple and easy to figure out, even if you forget how to do it. So this is FE style. A flexible pavement system is to be designed using the AASHTO structural number design method with the following criteria. If the minimum thickness of surfacing and aggregate base are used, what is the required thickness of the sub-base? Yeah, that English is not correct, but what is it most nearly? 4, 5, 6.5, or 8? So just using that structural number equation, overall structural number equals A1, D1. We're given information. We have 3 layers here. So A2, D2. We don't have any information about the drainage. We just have the coefficients, A3, D3. So our thickness, we're going to treat our thicknesses as D. These strength coefficients are A. So what are we actually solving for out of this equation? Yeah, we're solving for D3. So we're told if we use the minimum thickness of the surfacing, this would be layer 1, and the aggregate base layer 2, then solve for the resulting thickness of layer 3. And we're given our design structural number in this table, which is a little confusing. So we've got 2.5 equals 2 times, oops, I did it backwards. 0.44 times 2 plus 0.25 times 4 plus 0.10 times D3. So then you can rearrange and solve for D3. Oh, the 4. Those sneaky FE guys, they like to do those things. Anybody get anything? It seems reasonable, so we'll call that C. So then this example is using the table. So calculate the LEF of a loaded Class 9 truck that has a front single axle transmitting a force of 10,000 pounds and 2 sets of tandem axles, each set transmitting a force of 30,000 pounds. So you don't necessarily need to know what a Class 9 truck is. They give you all the information you need. So you've got one single, you've got 2 tandems, 2 sets of tandems. So Class 9 actually is a kind of a box truck. It usually says Walmart on the side of it. So we've got 10,000 pounds here, and each of these are total of 30,000 pounds. If we go to that table, we're just looking up the corresponding value for each of the 3. So what is the LEF for a single axle carrying 10,000 pounds? On page 307. 0.0877. And then our second, we have 30,000 pounds that is being supported by a set of tandems. So what is that? Nope. So that's the single.
658.
So we've got 0.658, and then there's 2 of them. So we've got 0.658 again. So what's this give you? This is some higher math right here. All addition with an A.
I think 4037.
4037? So what the load equivalency factor means is it's essentially 1.4 units of damage that this vehicle would do to the roadway. That's it for pavement. So topic area 3 is traffic capacity and flow theory. So traffic flow theory, these relationships are given on page 305. So hopefully you guys all remember the Green Shields model. Let me jump over to the next slide and kind of explain what's happening here, or hopefully refresh your memory of what's happening here. So these diagrams are given in the reference manual. So we've got speed versus density. We have speed versus flow, and we have flow versus density. So I always like to look at the speed and density chart first, because these all kind of work hand in hand. And these are for like freeway. I always like to think about an interstate. There's no traffic signals or anything. Cars can get on there and just go. So whenever the first car enters the roadway, what is the general speed of the traffic going to be? Is it going to be inhibited by the interference of other vehicles? If you're the only person on the roadway, what's prohibiting you from driving whatever speed you want? Yeah, or the law, or your compliance with the law. So the point is, when there's one car on the roadway, you can drive a maximum speed, a very high rate of speed. But what's the density going to be? If you're the only vehicle that's out there, what is the density of traffic on the roadway? Almost nothing, right? You're the only one there. So when one car is there, you're at this point on this plot because your density down here on the x-axis is low. So you're one vehicle per mile per lane, and your speed is basically uninhibited. So similarly, the flow rate, so the flow rate is vehicles per hour. If you're the only vehicle out there, then the flow rate is going to be also essentially zero. So high speed, very low flow rate. And then if your flow rate and your density are both low, you're at this point. So I'm going to circle this in red. So as more and more vehicles arrive, what impact is that going to have on speed? It's going to decrease because the more traffic that's on the road, everybody's trying to jockey and make sure they have a safe clear zone. So as the density increases, we're going to start going down this direction. So our speed's decreasing while the density is increasing. Until at some point we get down here to a point that's called the jam density. And that's when you essentially have gridlock and your speed would be zero. So when you get to this point, we're at the jam density, then we're at a zero speed. So similarly, so this is the same things happening over here. As the density increases and speed decreases, density is increasing, so we're getting more and more vehicles on the road, so the flow is going to keep increasing, right? Until a point where it reaches its max, because if the flow rate is vehicles per hour, as the number of vehicles increases, then the flow rate is going to keep increasing. But once it gets to this midpoint, the density keeps decreasing, but since the speed keeps decreasing, you end up with more cars going by, but they're going at a slower rate of speed. So therefore, the flow rate, which is vehicles per hour, or vehicles per time unit, actually starts decreasing, which is why we level out here and speed continues to decrease, but our flow rate actually starts decreasing. And so this VM here is referred to as a capacity. So it's like the maximum number of vehicles that we can get on a roadway from a flow rate standpoint. And then this flow density chart down here. So density and flow are both increasing. Density continues increasing, but our flow maxes out at this point. And so this is also VM, the same as this VM up here. So this is the general Green Shields model that's going on, is this relationship between speed, density, and flow rate. So now let me jump back here. So we just talked about these. So these equations, so this here is the equation that describes this line here. So this is just y equals mx plus b. So b is SF, so this is b. And then we have the slope of this line. It's going to be SF and DJ. So we've got SF over DJ, and then times density down here. So that is just giving us the general equation of that line. And then we've also got, this would be the relationship between speed and flow. So this would be the equation for this line here. So for any given value, oh, no, I drew it the wrong one. It's speed and density. So it's this equation here. So for any value of D, we can calculate the corresponding flow rate if we know SF and DJ. So the third equation is useful. So this is that VM value, VM here. This is referred to as the capacity of the roadway. Over here, they call it the maximum flow rate. So if we know DJ, we know SF, multiply those, divide by 4, they give us the max flow rate. So what they do not tell you here, and it's just dimensional analysis, is that flow is equal to speed times density. So flow is vehicles per hour. Speed is miles per hour. And density is vehicles per mile. So once you cancel out your miles, you're left with vehicles per hour. So it's just a simple dimensional canceling your units. And so if you have a density, you have a speed, multiply those together, and that will give you a corresponding flow rate. So V equals D times S. So let's look at this example. The mean speed on a road is given by the relationship V equals 60 minus 0.2 D. So first, which Green-Shields relationship is this? We've got three of them. We've got speed density, speed flow, and flow density. So we've got V in this equation, we've got D in this equation. So that means it is this speed density. And so that line is still in the format of Y equals mx plus B. So this is speed density. If the mean speed on the road during rush hour is 45 miles an hour, find the density of vehicles on the road. So we're just going to, since we know this is the equation of that line, we're just going to plug 45 in for V and solve for D. So I give you 15 divided by 0.2. Too late in the day. 75. So that'd be 75 vehicles per mile. And then the final one, determine the max flow for this roadway. That's going to be our VM, which was SF times DJ divided by 4. So how do we determine what SF and DJ are? What's this number? Our intercept, right? So we know from the relationship that that's the free flow speed. And then how can we find DJ? I don't remember if it's uppercase or lowercase. How can we find that value? How'd you get it? Yeah, so if you set V equals to 0, then you can solve for D. And so this becomes 60. Is it 300? Is that what you said it was? I trust you. Divided by 4. Whatever 18,000 divided by 4 is. 500. So again, the trick there is realizing what relationship it is and just using your math skills to determine what's the intercept, both y and x. A freeway lane has a volume of 1,400 vehicles per hour and an average vehicle speed of 45 miles an hour. The time spacing between vehicles center to center is most nearly what? So what are we given? What's the 1,400? Which variable? What are the units? So it's a V. We don't necessarily know if it's the maximum. It's just the V that happens to be in this particular instance, but it is a V. And we can tell that by vehicles per hour. And then we have a vehicle speed. I get my variables. Oh no, speed is S. Sorry. And then S is our 45 miles per hour. So we're asked, what is the time spacing between vehicles in seconds? So how do you think we can use this information to determine that value? So if we have 1,400 vehicles traveling down 3rd Avenue in an hour, what is the interval over which, what would be the interval between them if they were evenly spaced?
Just be a whole number.
Will it be a whole number? Is that what you asked?
They're evenly spaced. You're talking about the time spacing?
Yeah, well, so yeah, if you assume that that the space between them is uniform or even,
Well,
the average.
would you prefer vehicles per hour, vehicles per second?
Yep, and then one more transformation. Because we want to know, because that would be vehicles per second, but we want to know seconds per vehicle, essentially. So how would we do that conversion? So another way to think about it, how many seconds are in an hour? So if we got 3,600 seconds per hour, and we've got 1,400 vehicles that are passing through, I think 3,600 divided by 1,400 gets us there, doesn't it?
Right, that'd be
So maybe the better way to think about it is if we have 1,400 vehicles and there's one arriving every 2.6 seconds, 1,400 times 2.6 gets you to the 3,600, which is an hour, is another way to back into it. All right, the next topic is the peak hour factor. So what this does is it explains the variation of traffic within the peak hour. So whenever we're looking at traffic volumes, we usually have an AM peak hour, rush hour, and a PM rush hour, peak hour. And so we want to know within that peak hour, is traffic uniformly distributed, or do we have like a really high 15-minute volume and then the other 45 minutes in that peak hour? Because that can affect things like traffic signal timing and capacity analysis and things like that. So this is the equation that is given in the reference manual. So V is the total hourly volume, and then V15 is the peak 15-minute volume within that peak hour. So you basically have the full hour's volume, and then you look at the peak 15 minutes within that, multiply that by 4, and that gives you the peak hour factor. So just looking at this relationship here, what is the lowest this value can be? What is the lowest possible value that you can have for a peak hour factor? Lowest. Can it be 0? So if you have V over 4 times V15, so the scenario would be that if V and V15 were equal, what would this be? If V is equal to V15, what does the peak hour factor become?
0.25.
So it becomes 1/4 or 0.25. So if V and V15 are both 1, so the minimum peak hour factor would be 0.25. So what would the conditions be for V to equal V15? So how would your hourly volume be the same as your peak 15-minute volume? It's not very common in the real world. But every single vehicle at that intersection would have to occur in 15 minutes, and the other 45 minutes, there's nobody. Right, so then your total hourly volume would be equal to your 15-minute volume. So you might have that at like a plant or something where all the traffic, everybody leaves at shift change, and then nothing else happens the rest of the time. But this is the theoretical minimum. In reality, it hardly ever gets that low. So then what would the other end of the spectrum be? What would your maximum peak hour factor be? This is where, Harrison, you can kick in your answer. 1. So in order for this equation to be 1, V would have to be equal to 4 times V15, right? Because then we end up with 4 times V15. So that would mean that every single period was exactly the same. So that means you have no variation in traffic. Every single 15-minute interval has the exact same value. Because then your V is going to be equal to 4 times your V15. So this is a completely equal distribution. And this is a heavy peak. So in reality, the peak hour factor is usually in the 0.85 to 0.92 range at most intersections. When you're already looking at the peak hour factor within the peak hour is usually in the 0.8, 0.9 range. So how we actually calculate the peak hour factor. So we would be given the data in blue here. So somebody goes out and counts in 15-minute intervals. So from 6 to 6:15, there was 7:01, 6:15 to 6:30, there's 7:40. So if everything here is given, then to identify the peak hour, this 2946 is going to be the sum of the hour that starts at 6 o'clock. Then you would sum the hour that starts at 6:15, 4 intervals. And so you just keep adding all the way down through. And then when you've added up all your data, you go back through. And so when's my peak hour going to be? What's our highest hourly count? Which one? Yeah, so the highest value is the 3275, so that would make this our peak hour. So it would run from 6:45 to 7:45. So then calculating the peak hour factor for that period, we've got V over 4 times V15. So what's V going to be equal to? What's our total hourly volume during the peak hour?
3275.
3275. And then what's V15? So what's our highest 15-minute volume within the peak hour? So we're only looking at these 4. So what's the highest?
867.
Maybe I'm silly for it, but why did you choose the hour window? Like, how did you know to go to 7:45?
Because we need 4 15-minute intervals. What's that give you? Did you get?
0.93.
All right, so moving on to traffic capacity. So highway capacity manual, I'm sure you remember from transportation class. It's a glorious, painful procedure. They only give you information on the basic freeway segments. So page 303 and 304. If you might recall from transportation, the worksheet, the highway capacity manual worksheet. So this is not in the FE manual, but I put it in here just to hopefully jog your memory about it. In the upper left portion, I'm going to talk about this a little bit more, but the upper left portion, this chart is basically been converted into a table, which is what they're giving you in the FE reference manual. So we've got different free flow speeds, capacities, breakpoints. Each of these lines in this chart correspond to a different free flow speed. You've got the breakpoints, which are these points out here. And what these equations are allowing you to do is calculate a specific speed beyond the breakpoint whenever that starts to take a dive. Yeah, so here it is zoomed in. So jumping back to the Greenshields model, we had speed and flow rate. So speed and flow rate from that Greenshields model looked like this. So we had speed and flow rate. So as the cars increase, the speed is going to be impacted until you get to a max. So what you're seeing here is only this portion of that curve. That's why it kind of tails off. And so the Greenshield models, I should have mentioned this earlier, they're completely theoretical. If you look at real data, it's not like once you go from 1 to 2 vehicles, it's not like their speed's really going to be impacted. So it can keep building traffic up to a point, and then that's when it really starts to tail off, which is what's indicated by these breakpoints. So at 70 miles an hour free flow speed, it says the speed doesn't start to be impacted until you get at least 1,300 vehicles per hour. And then the more you add from there, then it starts to drop off a little bit more significantly. So that's all that's happening in this table. So they don't give you this chart on the FE, but realize that that's what's happening in this table, is that you can figure out free flow speed when there's nobody there versus whenever you get a lot of cars out there, what is the actual speed at which those vehicles are going to be driving. So you also get the free flow speed calculation. So FFS free flow speed, you start with a base free flow speed. FE gives you this default value of 75.4. Then you have this table for the lane width adjustment. So you can pull out this FLW to plug into this. So it's based on the lane width with the perception that, and those of you who are driving out on I-64 in the construction zone where they've got those barriers, it feels like you're driving in an 8-foot wide lane. You're certainly going to slow down. So that's essentially what this is accounting for. So base conditions of 12 foot, there's no reduction, but getting down to 10 to 11, then it reduces the driver's free flow speed by about 6.6 miles per hour. Same thing here, you've got the FRLC, which is the right side lateral clearance. Since this is a basic freeway segment, it's more the right shoulder that we're worried about, because on the left side, we're probably going to have a median. So we're only adjusting for that right side lateral clearance. And then our final term is this total ramp density. So if you're given information about the interchanges and the length of the roadway segment, you can calculate an average ramp density to plug into that equation. Then the last part is the flow rate. So you can calculate a flow rate using that equation. And then density. So density is equal to, so I lied earlier. So the Greenshields model, I said that they didn't give you this equation, but they're giving it to you. It's just in the highway capacity section. So this is still the density, flow rate, and speed relationship that we were talking about earlier. Density is what we're trying to ultimately get to with the capacity analysis, because density, we're always trying to find what's the level of service of the roadway. So once we figure out what's the density, then we can go in and correlate the densities to the particular levels of service. So the speed calculation, just to jump back. So we need free flow speed so that we know in this table which row to use and which equation. So this equation gives us S. In this equation, we need our VP value. So we're calculating VP here. So once we know VP to plug in there, we know S, then we can plug those into this equation to solve for D, which will give us our level of service. So all these equations are kind of interrelated to be able to ultimately determine the level of service. All right, so I see we're down to 10 minutes, and let me try to determine, well, actually what I'll do is I'll just keep blowing through. People who want to stick around can stick around, those who leave can leave, and if everybody leaves and you're tired of transportation, then that's perfectly fine as well. Unfortunately, I don't already have the solutions written out to give those to you. So traffic capacity, we have an 8-mile section of an existing urban freeway with 4 northbound lanes. With the following characteristics, we want to find the level of service. So first thing we want to do is find VP. So we need VP for everything. So jumping back to that equation, we have VP is V over peak hour factor times N times FHV. So V we see is our volume under the prevailing conditions, which were given as the peak hour volume of 2,800. We're given a peak hour factor of 0.90. N is the number of lanes, so this is 4 northbound lanes. And then we need FHV. So we have an equation for FHV, which is 1 over 1 plus PT minus 1. And if you're looking on that page, so PT is the proportion of single unit trucks and tractor trailers in the traffic stream. And then we have a table there to look up the corresponding value of ET. So it should be a 1 in the parenthesis. So our PT is given in the problem. Let's ignore the buses and just look at the heavy trucks. So we have 0.09 for our percent trucks, and then our ET value, we're given 2 possible ones. We have a value of 2.0 for level terrain and 3.0 for a rolling terrain. Which one do you think we should use in this instance? Think we're closer to level or rolling terrain in an urban freeway? Urban area, downtown area, we'll assume that it's a level area. So ET from that table is 2.0, and then we're subtracting 1. So whatever that calculation is will be our FHV that we plug into the equation up above. So then 0.917 will bring up here, and that will give us our VP. So this 2,800 vehicles was for all 4 lanes. We've now divided by 4. So this resulting, we're now passenger cars. So this FHV is converting from, it's accounting for the fact that trucks operate differently from passenger cars. And so our units are now passenger cars, PC for passenger cars per hour per lane. So that makes sense that we've at least taken 2,800 divided by 4, but we're also accounting for the peak hour factor and the truck factor, heavy truck factor. So that's VP. So now we need to determine what is S. So the first step for finding S is to calculate our free flow speed. So we're not given a free flow speed. So we will use the equation, which is base free flow speed minus FLW minus FRLC minus 3.22 TRD to the 0.84 power. So this is on page 303. So the default value for the base free flow speed is 75.4. What's our adjustment factor going to be for our lane width? So we have 11-foot lanes. So from that table, what reduction does that correspond to? Yeah, that's a little confusing. So the first line is greater than or equal to 12. I sort of think it is the 1.9.
We need to be conservative since it.
No, so I think what they want is greater than or equal to 11 and up to 12. Because 12 is certainly the base condition, which is 0. So if you assume that 12 is 0, then 11, if 11 is 6.6, then what's 1.9? So I'm going to assume that it's 1.9. That is, I'll have to bring that up to Dr. Waite, that is an extremely confusing table to have in here. So let's call it 1.9. And then what about our right lateral clearance? What is it from the table?
0.8.
Yep. So we've got 2-foot lateral clearance and we have 4 lanes in one direction. So from that table, we get 0.8. And then our TRD is the ramp density. So we have 4 interchanges over an 8-mile segment. So we would have 4 per 8. Let's see what the units are on TRD. So it's ramps per mile. So technically, an interchange has how many ramps? On a given direction. So if we're just looking at a northbound direction, each interchange is going to have how many ramps to contend with? 2. So if we've got 4 interchanges total, then we would have 8 ramps total divided by 8 miles. So that kind of cancels out. That's what we started with. Anybody else get something? Yeah, you can kind of ignore.
70.0.
That sounds better. Okay, so here's where, so we know our free flow speed is 70 miles an hour. We know our VP is 848. So let's go back and look at the table, this table here. So at a free flow speed of 70 miles an hour, is our speed going to be impacted at a volume of 848, at a flow rate of 848. How many cars do we have to have before this, at a free flow speed of 70 miles an hour? How many cars must be on the roadway for the speed to start breaking down?
1,300.
So look at the table. Don't look at my chart because I realize that my HCM worksheet is an older version. So what is it from the table?
Right? Like what?
Nope. So that's the capacity. So the next one over, the break point. So the break point is where the speed starts to decrease. So that's at 1200. We're only at 848. So we're still in the area where the actual speed is going to be equal to the free flow speed because we haven't reached a point. So our free flow speed in this instance is equal to our speed. If we were beyond the 1200, then we would plug in that V sub P in this equation, and that would give us our value of S to plug into the density equation. So density, so we now know S, we know VP, so we can calculate our density. So density is equal to, let's say it was, VP over S. So we've got 848 divided by 70. So 12.1 vehicles per mile. So then looking at the level of service table, what is 12.1, a density of 12.1? Technically, that's passenger cars. So a density of 12 is which level of service? B. So anything from 11 to 18, greater than 11, up to 18 is level of service B. All right, topic area 4 is fairly quick. It's traffic control devices, which the only information to give you is related to traffic signal timing. So we have 3 equations here, one for yellow time, one for red time, and this was a new one for me. This is minimum green time for pedestrians. So we talked about some assumptions for stopping sight distance. So in the context of traffic signal timing, we still have this driver reaction time T that also showed up for stopping sight distance, which we assume to be 2.5 seconds. What do you think is a reasonable reaction time for a driver's reaction for traffic signal timing? And it really only shows up here for the yellow time. What do you think is a driver's reaction approaching a traffic signal? Would it be greater or less than the reaction time driving on the open road, possibly looking for a deer or something to jump out in front of you? Should be less because as you're approaching the signal, you should be anticipating that it's going to change. And so the assumed, so it was 2.5 before, for signal timing purposes, it's 1 second. We also have L, which is the assumed length of vehicle in absence of any other information. We always assume 20 feet. And then we have deceleration showing up again. And same as what we use for stopping sight distance, we use 11.2 feet per second squared. So look at an example, calculate the yellow clearance interval if the design speed for the approach is 40 miles an hour. And this is some fancy animation, so don't blink. Everybody watch, I'm going to hit the button. This gives the driver enough time to react to the signal. That's disappointing. This is apparently one of the slides that I haven't updated for the wider format. He was supposed to have stopped back at the stop bar, not in the middle of the intersection. So looking at that equation for the yellow time, wherever it went. So we've got y, let's see if we've got y equals t plus v. Notice this is a lowercase v times 2a plus or minus 64.4 g. So let me jump back. So lowercase v, the units, as opposed to what we've been doing so far, which is all uppercase v in miles per hour, lowercase v means that we need the speed in feet per second. T, that reaction time we just talked about was 1.0, unless they tell you something different to use. So how do we convert speed in miles per hour to feet per second? So it's the same factor that was built into the stopping site distance equation. So we've got 1.47. That converts miles per hour to feet per second. Our deceleration is 11.2. And we don't have any information about a grade, so we can ignore that. Okay, so jumping back, the yellow time, whoa, what did I just do? That was weird. Notice that the yellow time, length of yellow interval measured to the nearest 0.1 seconds. I don't know if they'll try to trick you up on the rounding. If you calculate 3.625 seconds, these times, these clearance intervals are safety standards. So they're minimum values. So if you were going to round this to a tenth of a second, how do you think you should round it to make sure it's as conservative as possible? We would round it up to 3.7, because if we round it down to 3.6, then we're not fully providing the amount of yellow time that we designed for based on the speed limit or the design speed. All right, so the next one, let's see how its animation works. So the next one, we want to calculate the red clearance interval if the design speed for this approach is 40 miles an hour. Oh yeah, this is all jacked up. We don't even have a car. What is happening? So there should be a little car here going this direction. So what the equation, the red time, R is W plus L, even though it's lowercase, I'm going to write it as uppercase so you can see what it is. And so in this instance, W is the width of the intersection curb to curb. So you've got two different widths here. We've got 72 feet and we've got 48 feet, obviously not drawn to scale. Which width do you think we're interested in? Red time is assuming that as a vehicle enters an intersection, we want to allow enough time for that vehicle to clear the intersection. So what distance is this vehicle traveling through the intersection? It's going to be traveling the 72. We've got 72, assumed vehicle length of 20, and then we've got our speed again, 1.47 times 40, because that's a lowercase v. So the W plus the L is front bumper to back bumper, because we want even its back bumper to clear the intersection. So we need to travel the full length of the vehicle plus the width of the intersection at the design speed. What'd you get?
1.6.
1.6. Even?
That's 1.56.
Okay, so 1.56, and we've rounded that up to 1.6. All right, so the third one, this will be my first time doing one of these calculations for the pedestrian timing. Well, first time assuming that we're supposed to use this GP equation, because I've never even seen that equation before. At an urban pedestrian crosswalk, the initial walk signal is displayed for 6 seconds, after which a flashing don't walk signal is displayed. So that's how every single traffic signal works. The pedestrian walking speed is 3.5 feet per second, and the street to be crossed is 31.5 feet wide. At the end of the green time, the flashing don't walk is terminated, or it ends. So the minimum length of green that must be displayed is most nearly what? So we have an equation for minimum green time for pedestrians that is GP equals 3.2 plus L over SP plus 0.27 in PED. So the 3.2 is a constant. So large L is the crosswalk length, which we're given as 31.5. S sub P is the pedestrian speed. You're given default of 3.5 seconds. We're told to assume 3.5 seconds here as well. In PED is the number of pedestrians in the interval. So we don't have any information about that. So let's ignore it and see what we get. Calculate it. 12.2. So we'll assume that that's correct and call it 12.5. Yeah. I'm going to have to go search for the source of this equation. But at least you know how to use it. All right, the final topic area is transportation planning, and it has a few unrelated, two unrelated aspects. Safety used to be its own topic area, but they've combined it for some reason. So on the safety side, we're looking at crash rates. So for intersections, we have RMAV, roadway segments, RM, VM, which for some reason I've got these split out on different slides. So the next slide has the equations. And then we also can look at how many crashes would be prevented if certain countermeasures were installed with crash reduction factors. So on page 306, these are the equations you get. So you're told that crash rates at intersections use this RMEV. So RMEV is rate per million entering vehicles. So what's the rate of crashes per million vehicles entering that intersection? We have for roadway segments RMVM, the rate per 100 million vehicle miles. Some places there's an H in here, so it's RHMVM. And then we have the crash reduction. So we've got crashes prevented. So we have an expected number of crashes without the countermeasure. We have the crash reduction factor based on the countermeasure, so making some sort of improvement. And then we can account for any change in the traffic volume. Because you would expect with crashes, as the volume increases, the number of crashes is always going to increase. And so if you're looking at this crash reduction, so you install the countermeasures now and wait 5 years from now and collect some more data, you would expect the AADTs to change. So that's just scaling those accordingly. One thing I'll point out is if you have multiple countermeasures installed, each countermeasure will have its own independent crash reduction factor. So you don't just add those all together. This equation is how you combine multiple crash reduction factors, because some of them are going to eliminate the same types of crashes. And so you're going to overestimate your crash reduction if you just simply add them together. So at an intersection, we had 13 crashes last year. The 4 legs of the intersection had two-way ADT values given here. We want to calculate the crash rate. So we know that this is an RMEV, so because it's an intersection. And the RMEV is equal to A times 1 million over V. So A is the number of crashes in a single year at the location. So we were given that. So we essentially have 13 million on the top. V is the ADT times 365. So what does ADT stand for? Average daily traffic. So we want to scale our average daily traffic up to the annual volume. So average daily traffic times 365. So ADT here is the average daily traffic entering the intersection. So what we're given here is this approach. We have a two-way ADT of 9671, two-way here of 2893, 9506, and 2611. So since these are two-way, we only want the entering. So we need to take half of each of these numbers, take the sum and divide it by 2. So we're going to take 9671 plus 2893 plus 9506 plus 2611, all divided by 2. So that is our ADT. And then we're multiplying that times 365 to get our volume, total volume. I don't think he's doing this problem. I just think he's punching in his calculator.
That's 2.9.
So this would be 2.9 crashes per million entering vehicles. So that seems reasonable. These values are usually 50 or less, and so a low crash rate is somewhere in this neighborhood. A kind of a high crash rate would be in the 20s or above. All right, so now let's look at a segment. A 6.1 mile section of a road had 6 crashes last year. The two-way ADT was 755 vehicles per day. Calculate the crash rate. So RMVM is A times 1 million Oh, so they have fixed that. So I need to, they've eliminated this. So I need to update this slide. So if you look in your handout, this RMVM is now crash rate per million vehicle miles. So it's no longer crash rate per 100 million. This is no longer 100 million. This is 1 million. So look at the handout, not my slides. Everything else is the same. So we've got 1 million. So A times 1 million. Now on the bottom, instead of just a total volume, we want the VMT, which is the vehicle miles traveled, which takes into account the length of the roadway segment. So an intersection, we don't need to account for anything other than the traffic volume. But if we're looking at a 1 mile section versus a 100 mile section, somehow that difference in length needs to be accounted for, because again, as you look at a longer section of roadway, you would expect a higher number of crashes along that section of roadway. So the VMT is accounting for VMT equation given is ADT times number of days in the study period times the length of the road. So here, we're looking at crashes in both directions. So we want the ADT to remain the two-way ADT. So we've got 755. We're only looking at last year, so that's going to be 365 days. And then the length of road is 6.1 miles. So what's that give us for a VMT? 755 times 365 times 6.1.
1,681,000 and 7.
87?
No, just 7.
007. All right, so now we plug this in up here. We had 6 crashes times 1,000,000 gives us 6 million. Divided by that 1,681,007. Less than 1. Or no, it's less than 6. So we'll call that. So that's 3.5 crashes per million vehicle miles traveled. All right, so the last one for the crashes, we had a single location, 3 countermeasures with crash reduction factors of 40%, 28%, 20% are proposed. If the ADT before improvement is 7,850, ADT after is expected to be 9,000. Calculate the expected crash reduction if there have been 12, 14, and 13 crashes per year in each of the last 13 years. So we can calculate crashes prevented, so this is equation given, is equal to N times CR times ADT after over ADT before. So the first thing we need to do is calculate this combined crash reduction factor. So it's CR1 plus 1 minus CR1 times CR2 plus 1 minus CR1 times 1 minus CR2 times CR3. So we have 3 crash reduction factors. So we got 0.40 plus 1 minus 0.40 times 0.28 plus 1 minus 0.40 times 1 minus 0.28 times 0.20. So what's that give you for a combined crash reduction? .64? Okay, so then for N, we're going to average. So we've got, not that I need to write this out to solve the average, but 12 plus 13 plus 14, I could write divided by 3 should give you 13. And then we have our 0.65, and then our ADT after is expected to be 9,000 over the ADT existing is 7,850. So it should be 13 times 0.65 times 9,000 divided by 7850. So 9.7 crashes prevented. So they could also ask you what is the expected number of crashes after. And so then that would be 13 minus the 9.7. So you would, if you're start out with an average of 13, save 10 essentially, then you would be expecting 3 crashes per year after you implement the countermeasures. All right, we're on the home stretch. So the last and most painful part of transportation in general that nobody likes is the transportation planning process. That's not to say I don't like the transportation planners at the DOT. Planning is a very important section. But the people in the planning section are not doing this crap. So trip generation, I don't have a slide on this. If you remember from transportation class, trip generation is where you had the chart. You had a chart for commercial developments, gas stations, restaurants. And so if you had some information about the size of the facility, you simply had a chart where you could estimate how many trips are going to be generated by that particular facility. You don't have any information in the FE reference manual about trip generation. Trip distribution, though, they give you this gravity model on page 305. So in transportation planning, you can imagine the city being broken up into these different blocks or zones based on census information. And so trip distribution, you're trying to look at how many trips are going from one part of the city over to another part of the city. And that's what's happening with this gravity model here. The main factors, I can't imagine you would have a problem on this, but the socioeconomic factor, the K, you can kind of ignore. I've never seen it used. So then you're looking at trip attractions and friction factors that correspond to how far away, essentially what's your travel time between the different zones of the city. The example that I like to use that makes a little bit more sense is people are going to travel to a mall. They can either drive locally here to Barbersville, they can drive to Charleston, although that's not, I guess maybe I should change that to quarter G because nobody's going to the town center anymore. Or they can drive to Columbus. And so if you're looking to go for a true mall trip, even though Barbersville is the most convenient, maybe it doesn't have as many amenities. It certainly doesn't have as many amenities as going to a mall in Columbus. So even though it's farther to drive to Columbus, the fact that the malls are better there might increase the number of people that are driving there. And so population here is kind of a surrogate of how good the mall is. So Columbus has a lot more people, so their malls are going to be better. Charleston has more people than Barbersville. Notice this is not Huntington. It's, well, actually I have Huntington up here. But going to the Barbersville Mall, there's only 3,000 vehicles or people out there. So by using the gravity model, we're told that the friction factor is equal to 0.7 times the travel time to the -2 power. So this friction factor is going to be 0.7 times 15 to the -2 power. This one would be 0.7 times 60 to the -2, and 0.7 times 190 to the -2. And as long as the units are all the same, then this is just going to be used to scale. So let's just assume. Actually, give me what one of these are. So let's say that this is 0.00. It's going to be smaller, right?
0.301. 0.0019.
0.3.
Zero point zero 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 one nine.
Okay, so it is getting smaller. So 0 point, let's just say this one is even smaller. We'll put a 2. So the trip distribution, jumping back to the gravity model, we have a total of 10,000 shopping trips that we're going to distribute between these 3 areas. So we're solving for T, we know P. The attractions we're going to assume are related to the population, and then we just calculated the friction factor. So for this first one, we're going to have 10,000, and then we're just scaling. So this one would be 3183 times the friction factor of 0.003. And then the denominator is going to be the sum of all 3 of those. So we're going to have 3183 times 0.0003 plus 53421 times 0.000019. Sorry, I'm writing too small to see. And then plus 711,470 times 0.000002. So the denominators for all these are going to be the same. The numerator is changing, so you're essentially coming up with ratios. So you're ratioing out that 10,000 trip productions to each of the 3 locations. And so even though this friction factor based on travel time is small, it's kind of being offset by the population. So we won't go through all the details. Odds are you're not going to have this. I've never seen a sample question on the FE about this, but you never know. So the last one is mode choice, because trip assignment is also, they don't give you an equation for the trip assignment. But mode choice is given in an urban area. This is where this makes the most sense. Are you going to take a bus? You're going to walk? You're going to bike? Also, you can look at it from the standpoint of carpooling. So the Logit models, and I'm not even going to try to explain this outside of the context of an example. So these are the equations we're going to use, and I'll show you how to use them here. So we have a new office park that's being considered to start an express bus service for workers. A survey of office park commuters is conducted and found that mode choice is affected by out-of-pocket costs and total travel time. And that's summarized down here in this table. So we want to find what is the expected percentage of bus riders based on the parameters given, and what would the bus mode share be if the bus fare is reduced to 0. So we have this utility mode, and all we're doing is calculating the utility for each of the transportation options. So we have a utility mode for the automobile. So if you're going to drive yourself versus taking this express bus service, you're going to plug in the corresponding values for each coefficient. So A naught is 0.73. We don't have any out-of-pocket costs for the automobile, so we can ignore that term. And then the TTT is the total travel time. So we have minus 0.22 times 10.5. So that gives us a utility for the auto and then a utility for the bus. We don't have an A naught value, but we do have 0.47 times 75 cents. And then we also have the travel time for the bus, which is a little bit longer than the automobile. So what's this give me for my 2 utility values? Because we need those for the rest of the problem to make sense. What's the second one for the bus? Okay, so now let's jump back and look at the equations again. So the utility, this is just a generic form of the utility model. You're going to be given a specific equation if you have a problem like this. But now we need to jump down and use this equation. So P is giving the probability of selecting A mode. So auto mode A is given here, assuming that this example, they say you're choosing between auto and transit, but it's really two different types of transportation. So if we plug in, use this equation, we want to know what is the expected percentage of bus riders. So we can calculate the probability of bus equal to E to the negative 4.3, which is for the bus, the utility for the bus, divided by the sum of all the utilities. So this would be E to the negative 1.58 plus E to the negative 4.3. So we're just calculating a ratio here. So this will be a good opportunity to make sure you know how to use the exponential button on your Casio calculator. And if you get something greater than 1 or less than 0, then you've made a mistake. Because this is just a proportion.
Got 0.06.
So that is 6%. So we would expect 6% of the people to take this new bus service. So that's the answer to the first part. So the second part is, what would the bus mode share be if the bus fare was reduced to 0? So what would change if we were going on and doing the second part of this problem? So the 75 goes away. So we would still have that value would still remain the same, negative 1.58, but then we would have a new value here that is just the 0.22 times 18. So then you could redo this calculation with that new utility value, and you would seemingly get a higher percentage, because if you eliminate the bus fare, then it's going to become more attractive and you would have a higher percentage of people taking the bus. So the FE style problem for this mode choice is looking at HOV lanes. Anybody remember what an HOV lane is? What's HOV stand for? Well, maybe if you knew what it stood for.
Stay away from it.
What is it?
Some type of calculator.
Yep, but what do you think HOV stands for? High. High occupancy vehicle. So a high occupancy vehicle means that there is, well, some places designate that it's definitely not driving by yourself. So it's usually 2 or more vehicles. In some places, they're bus only lanes, which are really high occupancy vehicle lanes. But an HOV is a high occupancy vehicle lane. So to encourage more carpooling during the peak commute times, a metropolitan area is considering adding HOV lanes to a busy interstate segment. An existing transit route has a utility of 0.65. So utility is that U calculation that we just looked at. So instead of giving you the equation, they're telling you that transit, so the U for transit is equal to negative 0.65. Which is unaffected by the proposed change. If the existing non-HOV lanes have a utility of plus 1.2 and the proposed change introducing a carpool mode has a utility of negative 0.4, the percentage of trips expected to carpool is most nearly what? So we have utility, transit, we have the utility of non-HOV is plus 1.2. And then the okay, so they must be So this is minus 0.4. So they must just be adding the lanes, not repurposing existing lanes. So we have three modes here that we need to account for. So we want to know what is the percentage of trips expected to carpool. So we want to know what's the percent carpool. So our equation, we now have E to the negative 0.4 for the carpool, but our denominator, we now have to account for all three modes. So we would have E to the negative 0.65 plus E to the 1.2 plus E to the negative 0.4. So people have three choices. We have to take into account all three choices when we're calculating the percentage of trips that will be made by carpooling. All right, so that is 15%. So that would be answer B. So it looks like next year this might need to be broken out into three. Well, it's not quite enough time for three separate segments from a timing standpoint, because we were here 2 hours last night and almost 3 hours tonight. So what do you think would be the best method?
Might be better. 2 days for transportation.
So do you guys prefer coming and sitting for a longer time period or having to come more times for a shorter time period?
I'd rather have 2.5-hour blocks.